Hi, this is the assignment for land use and environment modeling. We built an agent-based modeling for COVID-19 propagation. As we all know, COVID-19 has had a profound impact on global public health, demonstrating the importance of understanding and mitigating the spread. Therefore, we have developed this modeling using NetLogo to simulate transmission dynamics of COVID-19 within the population. In terms of use case, the model can assist public health officials and researchers in studying the impact of various interventions and strategies on COVID-19 transmission. Also, it can be used to investigate the effectiveness of mask usage, social distancing measures, or other interventions. So first comes our interface design. The board consists of three parts, which are parameter setting, disease situation monitoring, and instant tracking plots. In parameter settings, there are three aspects. Disease setting decides the sick time, immunity days, and death rates. Typically, the interval range of sick time is set to 1 to 21 days, which means the time the person will be sick after being infected with virus. And immunity days refers to how long it takes for a person to recover from an illness and not get sick again. For the death rate of infected people, we set it in the range of 0 to 10% according to COVID-19 experiences. For protective measures, we mainly focus on mask usage and social distance. So basically, through two sliders, users can define the proportion of people wearing masks, as well as the probability of a person wearing mask will be affected. And demographic setting decides the population of healthy people and affected people in the first place. Disease situation monitoring shows instant figures of healthy, infected, deaths, immune population, as well as daily new infections and kills. While tracking plots gives a general idea of the change of population in each category. And this is the overall model simulation process.
So now we're going to talk about our model insights. For the trends in disease spread, it will quickly produce transmission, wait for the sick time to pass, and then gain a window period during which almost full immunity of the public is achieved. But the process will be repeated in each period. Among them, the immunity days basically are equal to the time interval between disease outbreaks, while the death rate determines how long it will take to reach the end of the world. In terms of protective measures, since the barrier condition is relatively simple, which means that within the social distance, only the mask is limiting the chance of getting the disease in the vulnerable population that does not wear a mask. At the same time, because of the rapid transmission, the population is almost simultaneously sick and immunized. Because of the limitation of social distance, patterns are more often in clusters. Finally, we want to talk about our reflections on the model. Overall, the transmission rules are rather conceptual and cannot be put into realistic context. Although the agent model is relatively too simple to represent individual activity patterns and autonomy. More specifically, first is that we assume the same viral transmission potency and virulence. However, in real life, the patterns change over time. Second, we build up simple obstacles, only including immunity, sick time, death rate, social distance, and mask. There are much more ways to hinder the spread of the virus. Third is some technical reasons. The problem that the infected population will suddenly change back to one is something we fail to fix. So thank you for listening.